Hello, everyone. Thank you for coming to this talk. I'm Sharat Ibrahimpour. Today, I'm going to talk about our work titled Caching with Reserves. This is joint work with Manish Purohit, Zoya Svitkina, Eric Wee, and Josh Wong from Google Research. Most of this work was done when I was an intern at Google Research last summer. What is caching? It's a classical problem in algorithms where we have a cache, i.e. a fast memory that can hold k pages of unit size. Pages are requested one by one. If the currently requested page is in the cache, then we have a cache hit, so the page can be served from the cache at zero cost. If on the other hand, the requested page is not in the cache, then we have a cache miss. Now we are supposed to fetch the requested page into the cache by evicting some other page. This incurs a cost of 1. In this animation, like I've just shown a small toy example of what would happen with a particular caching algorithm. A very popular objective in caching is to design a cache replacement policy that minimizes the number of cache misses. This problem is usually referred to as unweighted paging. Let me mention a few results that are known. If the entire request sequence is known ahead of time, that is, we are in the offline setting of the problem, then Bellidy's rule gives an optimal policy. What Bellidy's rule says is that whenever a cache miss occurs, evict the page that is requested furthest in the future. So the rule is trying to delay the next occurrence of a cache miss as much as possible. Since online algorithms don't know the future request sequence, so they are supposed to operate based on the knowledge they have so far. They have to make some deterministic or randomized page eviction decisions with the goal of keeping the number of cache misses low. To measure the quality of an online algorithm, we'll look at the competitive ratio metric, which is defined to be the maximum multiplicative gap between the cost of an online algorithm to that of its offline optimum. Tight algorithms are known for the online setting. There is a deterministic K competitive algorithm, and there is a randomized order log K competitive algorithm. A prominent result in this area is Fiat et al.'s randomized marking algorithm. What you need to know about like the order log K competitive guarantee is that it's some sort of a gold standard for caching algorithms. What are some drawbacks of traditional caching models or caching policies? They're not necessarily suitable for environments where we have multiple users. Take, for instance, cloud computing services. Users whose page requests occur infrequently don't reap as many caching benefits. If you think of like naively partitioning the cache among all users, then this strategy can be wasteful too, especially for global efficiency. Some recent works have aimed to maximize global cache efficiency by providing some sort of approximate isolation guarantees at user level. So what they do is that they promise that the cache hit rate for each user is at least as much as what it would be if the user was allocated its own isolated cache of some proportional size. Again, one can construct examples showing that this can be wasteful too. What we do in this work is we propose 2 simple models for caching with multiple users that generalize the standard model. We call these models as caching with reserves and public-private caching. I'll now formally state the models. In these 2 models, we have a cache of size K, and we have M disjoint agents. Agent I owns page set UI, and we'll call these set of pages as I pages. And the whole universe of pages is just the disjoint union of these page sets. For each agent I, we are given an integer ki. And at time t, page PT belonging to some agent IT is requested. Now, in the caching with reserves model, the constraint that we are always required to maintain is that there must always be ki many I pages in the cache for all agents I. And in the public-private caching model, the requirement is a bit more stringent. The cache is actually partitioned into up to m+1 caches. Up to m of these are private caches. So each agent has a private cache of possibly size 0. And then there's a shared public cache. Okay? The total size of all these caches is k. And the size of agent i's cache, private cache, is exactly ki. The constraint that we are supposed to maintain in public-private caching is that agent i's private cache can only hold I pages. Public cache is available to everyone. The objective in both these problems is to design a caching policy, cache replacement policy, that minimizes the total number of cache misses. Observe that the objective is still a global objective, but the constraints ensure that none of the agents are treated poorly. So the reserve constraint or the private caches ensure that there is some minimum level of guarantee that's some sort of a guarantee that's given to each agent. I'll now mention our contributions in this book. First of all, we show that these two models are equivalent up to constant factors. What we show is that given a C competitive online algorithm for caching with reserves, we can obtain a 2C competitive online algorithm for public-private caching. And in the opposite direction, we show that given a C competitive algorithm for public-private caching, we can obtain a 2C competitive algorithm for caching with reserves. This is a fairly standard, fairly easy proof. Next, what are our contributions for the offline setting of these two problems? Interestingly, we show that both these problems, both offline caching with reserves and offline public-private caching, these two problems are strongly NP-hard. Observe that this is in contrast with the basic model, where Bellidy's rule gives an optimal solution. This hardness result is based on a reduction from a variant of 3SAT, where we are interested in satisfying assignments with exactly half of the variables set to true. This reduction is quite involved, so we won't get into the details. Given the equivalence of these two models, we focus just on the caching with reserves problem. Our next result is a two approximation algorithm for the offline version of caching with reserves. And this result is based on a generalization of Bellidy's farthest in the future rule. Next, we consider the online version of caching with reserves. Here we give a 2 times log k competitive fractional algorithm. What I mean by a fractional algorithm is that the algorithm is allowed to partially hold on to a page. So if the currently requested page is in the cache up to a portion of 60%, then the cost of fetching the remaining 40% of this page is 0.4. This algorithm is based on the primal dual framework, and the analysis closely follows the analysis of Bansal et al.'s algorithm for classical weighted paging. Complementing theorem 4, we also give a randomized integral algorithm with a similar competitive ratio. I'd like to remark here that the rounding technique that we use to convert this fractional algorithm to the integral algorithm, this does not run in polynomial time. The proof is, again, fairly natural. In the remaining time, I'll focus on one of our results, which is a 2 approximation for offline version of caching with reserves. The goal is to devise a caching policy that always maintains at least ki I pages for all agents I. And we want to do this for all times. The main idea in our algorithm is that we'll be running 2 rounds of abilities for this in the future algorithm. First, we'll run it at the agent level. Here, what I mean is that we'll run it at the agent level for the agent whose page is currently requested. And then we'll run some sort of abilities rule at the global level. I'll need some notation to describe our algorithm and analyze it. I'll use alg and opt to denote our algorithm and the optimal algorithm. And I'll use n and n star to denote the set of pages in alg's cache and opt's cache. We'll always maintain partitions of our cache into m+1 parts. So the algorithm's cache is split into m+1 parts, which I'll denote as disjoint union over nj's, and same for the optimal algorithm's cache. The property that we'll always maintain is that nj and n star j consist of exactly kj pages that belong to agent j. And we'll also maintain the property that n0 and n0 star consist of the remaining pages. I'll use the notation k0 to denote k minus summation of kj's. We'll also assume that initially n is partitioned arbitrarily and n star is identical to n. I'll use rank of q to denote the time at which page q is requested next. Intuitively, what our algorithm is going to do is it will try to ensure that the sets nj consist of pages with low rank. Okay? That is, pages that will be requested in the near future should be in these sets nj. I'll now describe our algorithm. At time t, page p owned by agent I is requested. As of now, the rank of p is t. So currently we are at time t and the current page request has come in. And we need to process this page and then later on we'll update its rank. The algorithm has four parts. First, I'll describe what the algorithm actually does. What it does is, if the page is in the cache, that is, it is either in ni or n0, then the page is served from the cache and we are done. Otherwise, we'll evict some page q0, which I'll define shortly. We'll fetch p in that location and serve the page p. So how do we make the decision for which page to evict? Here's what we'll do. We'll run a round of agent level ability. What we do here is we add page p to the set ni and remove it from the set n0. If the size of ni exceeds ki, recall that ni was previously of size ki. So if adding this page increased its size to ki plus 1, then we move the page in ni with maximum rank to n0. So this again brings back the size of ni to ki. Observe that this entire block is not executed if p was already in ni. Next, we'll run a round of global level ability. What I mean by this is, if the size of n0 is k0 plus 1, this would have happened if certain conditions are met. But if the size of n0 is k0 plus 1, then we'll remove the page q0 with maximum rank. This is the page q0, which our algorithm will evict. Again, this entire block is irrelevant if p was already in ni or n0. Our last step in the algorithm is to update the rank. So we'll set rank p to be the time of p's next request. Okay? So that's the whole algorithm. How do we show that this algorithm is a true approximation? We'll do this using a potential function argument. This potential function argument is inspired by the work of Bansal et al. who very recently gave a new proof of optimality of Bellidy's rule based on a potential function argument. Our analysis is based on generalizing this potential function argument. For any positive integer s and any j in 0 through m, I'll use little nj of s to denote the number of pages in capital Nj with rank at least s. Similarly, I'll define n star j. Okay? Let me use a table to define these notions. Okay? So here I have the ranks in the first row. In the second row, I have an X mark if there is a page with that rank in Nj. Similarly, I have X marks for n star j. Little nj of s is simply the number of X marks that you see at this point or to the right of this point. Okay, so this is 4 here. Here also it's 4. If you go here, there's only like 3 more X marks to your right. For any j from 0 through m, we'll define the potential function phi j to be the maximum over all ranks, the difference between little nj and little n star j. For instance, in this example, phi j is 1 because the diff is 1. The maximum diff is 1. And observe that the potential phi j is always non-negative because for a rank large enough, both these quantities are 0. What a positive phi j indicates is that opt is better positioned. So there are pages that are going to be requested where opt might get an advantage. That's what it means. The overall potential that we use is capital phi, which is just the sum of these little phi j's. Okay, overall j going from 0 through m. Okay. Now let's go to the analysis. What we'll show is that the cost of the algorithm up to time t plus the potential at time t is at most twice the cost of the optimal algorithm up to time t. Now, since at time t, the cost of both algorithms and the potential is 0, it suffices to show that in each time step, the change in the algorithm's cost plus the change in the potential is at most 2 times the change in the optimal cost. Okay? And to make the analysis simpler, what we'll do is we'll further split each time step into 6 substeps. The 6 substeps are shown below. So here's what we are going to do. So in step 1, we'll process addition of p to both ni and ni star. In step 2, we'll remove p from both n naught and n naught star. Okay, recall that like ni stars correspond to the partition of the optimal algorithm's cache. Okay. In step 3, we'll ensure that these sets ni and n star I, they have size exactly ki. So for our algorithm, if the size of ni is ki plus 1, then we simply move the maximum rank page from ni to n naught. That's how we fix the cardinality constraint. However, for the optimal algorithm, we'll be moving some carefully chosen page from its ni star to n naught star. Next, in step 4, we'll allow the optimal algorithm to make its move, and we'll also ensure that its n naught star has the right cardinality. So if the page is in the opt's cache, then opt serves page p at 0 cost. Otherwise, it must be the case that n naught star has size k naught plus 1. So in this case, we'll again like choose like some page carefully, and we'll perform like some movements and evictions based on this. In step 5, we'll allow our algorithm to make its move. If p is in our algorithm's cache, then we serve it at 0 cost. Otherwise, what we do is we simply evict the max rank page from n naught. This again brings back the size of n naught to k naught. In step 6, we'll update the rank of p to be the time of next request for page p. Now observe that the way I have partitioned steps, the change in optimal algorithm's cost only happens in step 4. In this step, we will be able to pay for change in the potential function up to say 2. Okay, so that's what we can pay for, because like we have 2 times opt on the right hand side. Also observe that the cost of the optimal of our algorithm changes only in step 5. That if this condition holds. Since we don't have any payment available from the optimal algorithm, we must show that this cost can be compensated by a drop in the potential. And in steps 1, 2, 3, and 6, we must show that fee does not increase. A quick remark, steps 3 and 4 are the involved ones. Rest are fairly easy to analyze. Now let's get to the analysis. So in the first step, we add P to both Ni and Ni star. And we want to show that the potential does not increase. Okay. Since Ni and Ni star are the only sets that change, it suffices to just argue that delta phi is at most 0. Let's consider a simple table here. Now we have 4 cases. In case 1, let's say if the page belongs to both Ni and Ni star, yeah, then nothing changes. Okay, so the sets don't change. In case 2, let's say P is not present in either Ni or Ni star, then observe that putting X marks in either of these 2, in both these spots, does not change the diff between Ni and Ni star. So phi again remains unchanged. In case 3, suppose that P belonged to Ni, but it didn't belong to Ni star. Then in this case, observe that Ni star may only go up. Adding an X mark here only increases Ni star. So phi does not increase. Now let's look at the hard case when the page P is in the optimal algorithm's cache, but it's not in our algorithm's cache. We claim that phi does not increase. This is because if you were to add an X mark here, then the diff at this point is the same as the diff at time t+1 before the page was added. Okay. Now let's look at the diff here. The number of pages to the right of time t+1 is exactly ki, because that's the size of Ni. Whereas the number of pages to the right in this row is ki minus 1, because this page gets excluded. So the diff was already 1. And observe that the diff, when you add an X mark here, at the diff at time t becomes 1 after adding p. So phi could not have increased. A similar analysis for step 2 shows that the potential does not increase. Yeah. Now let's look at the harder case, which is step 3. So here we are trying to ensure that the Ni sets have size exactly ki. So if cardinality of Ni is ki plus 1, then we'll move a max rank page from Ni to N0. Whereas if the optimal algorithm's Ni has size ki plus 1, then we'll move some carefully chosen page q star I from Ni star to N0 star. In the first case, when both of these sets have size ki is trivial, so we'll ignore that. In the second case, consider the setting where Ni has size ki plus 1 and Ni star has size exactly ki. So what happens here is that adding qi to the set N0 may increase phi naught by 1. So we will need to argue that the potential phi drops by 1. So how do we show this? Let's look at the difference between NIT and Ni star of these. Okay. Then this diff is 1. Why is this the case? Simply because Ni has size ki plus 1 and Ni star has size ki. Okay, so which means that the potential phi is already at least 1. Now, removing a max rank page will definitely cause a decrease in every diff which was positive to start with. So that's why like the potential phi will drop by at least 1, and this can pay for an increase in the potential of phi naught. Overall, the capital phi potential does not increase. Next, consider case 3, where Ni has size ki, and I star has size ki plus 1. In this case, what we'll do is we'll choose qi star to be the second lowest ranked page in Ni star. Note that qi star is not equal to p, and that adding qi star to n naught star may only decrease the potential n naught, phi naught. Okay. Now, observe that the diff at time t plus 1 between Ni and Ni star is -1. And as we keep moving to the right, the diff can only decrease. And the first moment when we hit qi star, the potential, the diff can increase, but because it started at -1, at best it can become 0. So that's why, and after this point, anyway, this page, the eviction of this movement of this page does not influence the diff later on. So that's why the potential does not increase in this case. Now let's look at the hardest case in the analysis of step 3. Now we are in the setting where both Ni and Ni star have size ki plus 1. Now there are, we'll consider 2 cases. Either the rank of qi is strictly less than the rank of, is at most the rank of qi star, or it's the other way around. So the 3 pages of interest to us are the max rank page in n naught, the max rank page in n naught star, and the second lowest ranked page in n naught star. Okay. So in the first subcase, where the orange page is before the green page, what we do is we move the page qi to n naught, and we'll move the green qi star page to n naught star. Now observe that any increase in n naught star is offset by an increase in n naught star. And also, any decrease in NIS is offset by a corresponding decrease in Ni star of S. This is simply because of the relation between the ranks of these 2 pages. Next, consider the other subcase, where the rank of qi is strictly greater than the rank of qi star. In this case, what we do is we move qi again to n naught, but now we move page q prime to n naught star. So any possible increase in phi naught is offset by a decrease in phi. Again, this can be seen by doing a simple like a case analysis with like all possible combinations, but that's the main idea in showing that the potential does not increase in this case as well. In the interest of time, I won't go into the details of the analysis of the 4th, 5th, and 6th step, but I'll just quickly like show the slides of these steps, and an interested reader can pause the video and watch this. Now, with this, I'll conclude my talk. So in this work, we introduced 2 models of multi-agent caching. One was based on reserves, and the other was based on like some sort of a public-private framework. These 2 models are equivalent up to factor 2, and both of these problems are strongly NP-hard. For caching with reserves, we gave a 2 approximation algorithm in the offline setting, and an order log k competitive fractional algorithm for the online case. And we also gave a randomized order log k competitive integral algorithm, which does not necessarily run in polynomial time. I'd like to mention a few open questions that arise from our work. The very first question is like, is there a polynomial time integral algorithm that is order log K competitive? Next, is there an integral algorithm which is based on the marking strategy? Here, marking strategy is I won't describe what the marking strategy, but it's a very simple integral algorithm with competitive ratio order log K, and that works for the unweighted paging setting. So can we obtain a similar algorithm for caching with reserves? The third question is, can we extend our results to the settings where the cost of fetching or editing a page or the size of a page is not necessarily one? With this, I'll conclude my talk. Thank you for your interest.